In this video, we will use the definition of the derivative to calculate several more derivative examples. So the first thing we would like to do is use a definition of the derivative to differentiate the function 3x squared plus 4. So just writing down the definition of the derivative, which is always our starting point, f prime of x is the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x over h, and the first thing we need to do is take care of the function evaluation, f of x plus h. So our function is defined wherever we plug in for x, it becomes 3 times that quantity squared plus 4. The quantity we're plugging in is x plus h. So f of x plus h is 3 times the quantity x plus h squared plus 4. And then we are subtracting away the entire function f of x, so we're subtracting away the quantity 3x squared plus 4, and this is all divided by h. And as we've seen with our previous examples, before evaluating the limit, the first thing we must do is algebraically simplify. So just working our way across the top and distributing out the x plus h quantity squared, we're going to have 3 times the quantity x squared plus 2xh plus h squared plus 4. And then in the second term in the numerator, the minus sign needs to distribute through. So minus 3x squared minus 4, and this is all divided by h. And we're going to see some nice cancellations once again. Plus 4 minus 4, and remember the 3 has to distribute through the first term, and the 3 hits the x squared, and we'll have a 3x squared and a minus 3x squared. So this is leaving us 2 terms on the top that do not cancel, a 6xh plus 3h squared, and this is all over h. Each term contains an h, so we will cancel off the h, which is present in each term, and this results in the limit as h approaches 0 of 6x plus 3h. 6x plus 3h is a polynomial in terms of h, so we can use our substitution property, which tells us to plug in the value h equals 0. That gives us a limit of 6x plus 0, or simply just 6x. So in this problem, the derivative is 6x. So one last example of using the definition of the derivative. In this example, we will differentiate the function square root x. So our first step is to write out that definition. So the limit as h approaches 0 of the difference quotient. In order to do the function evaluation, we're plugging in x plus h into our function. So each x needs to be replaced with that quantity. So this becomes a limit as h approaches 0 of the square root of x plus h minus f of x, all divided by h. And once again, from our experience in Chapter 1, this is a familiar looking limit. We cannot simply plug in h, and really the only algebraic manipulation that I think would help us here is this technique of multiplying by the conjugate over the conjugate. So we're simply multiplying by 1, so we do not change the value of the limit, and we're doing so in a fancy way that allows the numerator to simplify very nicely. So because it's the conjugate over the conjugate, we have this difference of squares formula. In the top, we end up with the first term squared, so that would be x plus h, minus the second term squared, which is just an x. And this is all divided by the h in the bottom, multiplied by the square root of x plus h, plus square root x that we are multiplying it by. X minus x, h and h cancel, and we're left with a nice looking limit, the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. And from our experience evaluating these, we've seen we'll take the limit of the top over the bottom. And when we take the limit of the bottom, we'll break it up in terms of the limit of the first term plus the limit of the second term. And in the first term, we'll go ahead and use a limit law that allows us to plug the limit inside the square root. And in terms of the limits that we have to evaluate, well, the limit of a constant is always at constant. With respect to h, 1 is a constant, and with respect to h, the square root of x is also a constant. So we're going to have 1 in the top, our second limit in the bottom will be square root x. In terms of the first limit which remains in the bottom, x plus h is a polynomial in terms of h, so we can use the substitution property and simply plug in h equals 0. So the value of our limit, in this case what will be the derivative, is 1 over 2 square roots of x. So for the function f of x equals the square root of x, f prime x is 1 over 2 square roots of x. This is a function that we will frequently differentiate, so this is going to be a formula that we will use often. So it is definitely worthwhile to remember that the derivative of the square root of x is 1 over 2 square roots of x.